Ladies and gentlemen, we will go for the third session today, which is GaN, which maybe talk about surfing in the USA. The Beach Boys are all on stage. So Thomas Neyer will be the first one. Let us know what he can tell us about GaN. Thomas, go ahead.
So, good afternoon, everybody. I'm sure you are interested what is the Infineon point of view on the GaN developments, and so I'll here give you a couple of quick glimpses on how we see the world rotating. First one, obviously the silicon dominance we just talked about is really still here. Yeah, the white band gaps are coming, but they're coming slowly. The biggest growth rate these days is from gallium nitride, and this is why I think this is where we see the most exciting parts of challenging to be sold. Of course, this is where silicon carbide was possibly 5-8 years ago. So we see they are still growing strong in the automotive, and the silicon part is actually not shrinking. Yeah, it's also still alive and is, for the right applications, definitely the right solution. When it comes to gallium nitride, this is what we see here, and this is about the next couple of years, right? The next 5 years. We see, and everybody knows that, right? You can buy GaN chargers today, which do 100 watts and are tiny like a thumbnail. And this is the red color here. The green color is silicon. There is something in between, which is the silicon carbide part. So we see, again, already dominating on the high voltage side, especially PFCs in application for the fast switching lags, and GaN coming very quickly. Medium voltage, here still low medium voltage MOSFETs dominate, but here also it will be very quick where low medium voltage GaN will replace, right, at higher switching frequencies and higher power densities. Then the whole topic servers, yeah, they are getting more traction now in the AI world, and here, of course, we see already silicon carbide helping to increase power density. Eventually, there is no way than using also gallium nitride here on the high voltage side. Onboard chargers slowly go silicon carbide and will transition by end of the decade into gallium nitride markets. And we see already development projects for motor control. This is more low voltage, but also here you see medium and high voltage coming almost at the same speed, and residential solar also starting to use, replace even silicon carbide with gallium nitride on the high voltage side. And of course, in microinverters also a lot MOSFETs turning into gallium nitride. So this is something which we observe, where we have active engagements going on. You might have heard also GaN systems acquisition. So a couple of words to that. Infineon has, in the meantime, fully merged with the GaN systems group. We do joint development, and we will talk about it. What is it actually? It combines complementary skills. We, for instance, believed, okay, our focus is technology. The GaN systems guys came with a lot of application understanding, customer relationship, existing business. Then, of course, with our strong muscle in terms of sales team worldwide, we are able to accelerate this growth even. And then, of course, also our in-house manufacturing capacity in conjunction with an external supply chain in foundries makes a lot of sense. So this is really the rationale behind. And Infineon technologies, whether they are legacy GaN systems or Infineon, they are all the same when it comes to best-in-class quality. Yeah. So gallium nitride penetrates the market, especially now also industrial markets and in the future automotive markets, because their quality is equal or superior to incumbent solutions in silicon and silicon carbide. And so what we do is we do a lot of accelerated testing in order to find out the intrinsic failure models of gallium nitride HEMTs, but also we do a lot of early life failure studies in order to make sure that there are no early failures in the field, and this we call the extrinsic. So we do this all in accelerated mode, and then we can really, before the use condition, give you a lifetime model, and you know what type of performance you're gonna have. In addition, of course, we also, for new applications, we do safe launch projects, where we continue to do extensive testing over the first couple of quarters, and then, of course, keep this in a quarterly monitoring scale in order to ensure nothing drifts and the GaN technology stays working. And then we do the same for the in-house, of course, where we do the fab, the test, and the packaging in-house, but also we have the same complementary external supply chain. So I think we are really also ready and willing to do major ramps, very steep ramps, and also the technology at this point of time is ready. You have heard the announcement about our new 8-inch technologies, both in high voltage and medium voltage. They are all rolling out as we speak with this setup. So in summary, the Infineon Llew, we have a great portfolio. It is a perfect fit because we have now the joint R&D force and can develop a very innovative solution. We have the application know-how. We do a lot of in-house testing, also dynamic screening. Our roadmap is now accelerated with the additional muscle of GaN systems. And of course, we focus on our core business, which is our manufacturing expertise. With that, I'm done.
Thank you, Thomas. Alex, it's your turn now.
Thank you very much. Let's see. Okay. So, let's see. There we go. I'm going to talk a little bit about some of the key applications that have been driving GaN volume in the last year and a half or so, and then also we'll look at where it's going in the next few years. So one of the biggest drivers right now is AI servers. And if you see a Chat GPT box or whatever it is, it's going through an AI server. About 80% of those are NVIDIA, but 100% of them are powered by GaN devices right before the chip. There's about one of our GaN-based power supplies in front of every AI server chip, whether it be from NVIDIA or AMD or from any of the other manufacturers out there. So that's been a big driver. Two of the several power supply companies that are doing it are shown here, MPS and Flex. They both have high volume 1 kilowatt power supplies for AI servers. As I said, you know, there's a few others that won't be named right now, but they also produce for these AI servers, and it's all in very high volume right now. It's kind of amazing, and it's probably going to continue because we're just now beginning to see the Alibabas and Amazons and Metas and Microsoft and Alphabets get into the game, and they all are trying to take that market share away and create new markets. So it's a big sweep up right now, and these are all 100 volt and 40 volt chips going into this. So far, 100% of them are being serviced by EPC. I imagine that'll change over time. Just to show you where the technology is, right now, you know, this was a few years ago, generation 5, which was 18 millimeters squared. What does that mean? It means that a 1 square millimeter chip at 100 volts will have 18 milliohms. It's a gauge of chip size. About a year and a half ago, we introduced our Gen 6. There it is. And it's 12 millimeters squared, so we're making progress, but it's still 150x away from that blue line, which is the theoretical limit for gallium nitride. Of course, we're far away now from the theoretical limit for silicon, and the farther away we get, the faster we accelerate that curve that you saw from Infineon of GaN versus silicon. Gen 7 is coming out late this year from EPC. And again, that takes us another step further at 100x away from the theoretical limit at 7 milliohm millimeters squared. But what does this mean? And in order just to illustrate what all this means in a AI server, let me show you some of the real, actual measured curves. So this is the power loss of a kilowatt DC to DC converter, like the ones I showed you a minute ago. This is the power loss in those DC to DC converters for various different devices. And included here are the Optimos 7, the new Optimos 7s. On the left-hand side are Generation 5 devices, and in the middle are Generation 6 devices. Now, the best one out there today is shown, I show you on the line. It uses the EPC 2071. And that's in very high volume production. And you can see that line shows you the power loss of the entire system. The blue bar is the power loss in the devices, very little. But the rest of the system is what drives a lot of the costs. There, of course, is Optimos 7. It's above the line. Excuse me very much, but it's true. And there is our new Gen 6. So it's actually below the line, although the power loss in the device is much less. So that means that there's some options in actually shrinking the primary side, because this Generation 6 device is it's in a package, which some people prefer, and the total package device is smaller than the chip scale device in the prior generation. You can see that on the right. The prior generation best in class was 10.35 square millimeters. The packaged GaN device is 10 square millimeters, and the chip inside it is 7 square millimeters. So you can see how the devices are getting smaller, and with that, of course, you drive cost. Let's go a little further here. So now I'm showing you next generation, and these are the ones that we launch at the end of this year. Same graph, except now I've added the Gen 7 devices. I draw that same line on the 2071, which is the benchmark today. And if you look at the EPC 2071 that I showed you before, 10.35 square millimeters, that's where the line is drawn across at about 22.5 watts. And there it is. And Gen 7 devices, right there on the far right, that device is 5 square millimeters. And again, in a 10 square millimeter package. So you can see that, that now we're getting to less than half the size of devices that are in the volume production. So there's a factor of 2 improvement here coming in just this year. And that's going to be designed in very quickly. Just to look at that, there's a drive also to higher frequencies. And I'm showing you a chart where the horizontal axis is the frequency, the vertical axis is the power loss of the system, not the device, but of the system. And this is your best in at high frequencies in Optimos 7. That's the best at low frequencies, so the 1 megahertz line, the vertical line. And that's our best Gen 7 performance. So you can see it's much, much lower. It's about, you can put about 600 watts more out of the power supply with the Gen 7 device than you can with the prior generation's devices. And there's the lowest cost. And this little device is only 2.5 square millimeters. And it has about the same output power as that 10.35 square millimeter device that's the highest volume one today. So we're going pretty fast. This is not the end. As I said, we're 100x away, and I am driven to get there. Thank you.
Thank you, Alex. Now, our next speaker will be Philip Zuck. Philip speaks for Transphorm.
Testing. Hello, everyone. Thank you very much, Bodo, for having me here this year again. So basically, we look at as gallium nitride as a future-proof technology, right? It's in RF, it's in optics, it's in LEDs, and I've talked a lot about our 1200 volt technology that we're going to be sampling over the next 3 months, and short circuit protection and 4-quadrant switch. But today I really want to talk to you about how we're really enabling customers versus challenging them through the flexibility and performance of our technology. So this is kind of my mantra, and this is a slide that I use on many of my presentations. It's basically why Transphorm. And being a vertically integrated organization where we own the design, the process, and the epi gives us the ability to give our customers with the best in quality reliability with performance to match, but also the drivability and designability of the technology. So what I'm adding here is basically the flexibility to the designability. And that gives us, that really ties the three-legged chair into kind of a real solid, best-in-class reliability with over 25 million devices in the market today, over 300 billion hours of field reliability data. Yes, we do our own internal end of life and intrinsic and extrinsic reliability, but ultimately what customers want to see is what's in production today, and we have over 300 billion hours of field reliability data with a fit rate of around 0.05, which is 0.05 failures per billion hours. So let's talk about the flexibility. And this is going to be more on not really the technology, but more on the packaging, but what's enabled by the technology. So what we have here is, on the left-hand side, we have our, we have our standard, our traditional PQFN devices. These are what we call our performance package. And we call them a performance package because the actual paddle is 15% larger than the standard industry 8x8 and 5x6. And ultimately, this is almost 50% of the size of the die. It actually covers around close to 47% of the die. And we have larger pins. One of the issues with that has been basically talked about and written about, especially in silicon superjunction, is board level reliability of PQFN 8x8s and 5x6s. Customers that use power supplies that have 8 layers of FR4 board, FR4 board 8 layers, and when you start doing some temperature testing on those, you literally can rip the pins off the package. So what we've done is we've actually worked with our customers to increase those pins for increased board level reliability, if that's what customers are looking for. We also have the standard, industry standard 8x8 pin, 5x6 and 8x8 packages. And the nice thing about this is that it's drop-in with any E-mode technology in the market, as long as it's a discrete E-mode device. And we can either be driven by a standard silicon driver, whether it's a off-the-shelf driver or a silicon controller for low power, or a eGaN driver that drives up to 6 volts. And how do we do this? Very simply, by adjusting the low voltage MOSFET. So what you have here is you have a D-mode device that wants to operate and normally on. We make it into a cascode with a low voltage MOSFET that drives it. So we can control that basically with the 2 volt threshold here, which is fully on, around 5 volts, so you can drive it by any E-mode driver in the market. Even though our gate charge is a little bit higher than what you would get out of a PN junction or a Schottky, there's still no problems. Or we can use a 4 volt driver. And this is basically just driving like a super junction device, right? 4 volts plus or minus 20 on the gate. Again, highest reliability, most robust gate in the market, and can use any driver out there. And not only do we have the surface mount, but we also have the flexibility of replacing 2 PQFN devices with a TO220 or a TO247, right? This gives customers the ability from 500 watt and above to actually reduce their part count, increase reliability, reduce cost, and also increase power density. So this is, again, another advantage of the cascode because it's able to operate as a 3 leaded terminal, does not require a Kelvin source. We use a Kelvin source is because that's what customers want, and that's what E-mode requires, so we provide it. And then on the TO247, the nice thing about having a 4-leaded technology package today is it's drop-in with silicon carbide, and it's drop-in pin-to-pin with silicon. So our customers can basically take a board that they have today, pull out what they're using, whether it's silicon or another wide bandgap technology, and basically drop it in and turn it on. Again, 4-volt threshold. Drive it with a traditional silicon driver and with a QG of 2 to 3 times lower than silicon carbide. So the performance thing I want to talk to you about, and this is actually looking into the future because what silicon carbide has been doing, and they've been doing a great job by increasing the, or improving the interface between the silicon and the silicon carbide, the silicon and silicon dioxide channel. So what they actually have is they've traditionally had a temperature coefficient of a really low, about 1.4. And this has been one of the competitive advantages when it comes to high temperature conduction losses. And this is in a 3rd generation technology. But as they move to their newer generation, what's happening is that they're basically making that interface better, but now physics is stepping in. And physics is saying, well, okay, that's great, your mobility is going higher, but your TCR is now going higher. So now that 1.4 becomes 2. So that now limits their advantage against GaN. As you can see here, with our 15 milliohm at 175 degrees C, the TCRs are now the same. So we haven't done anything, but as silicon carbide evolves their technology, their conduction losses are actually taking a hit. So with a mobility that's twice silicon carbide, and now a similar TCR over temperature, and a larger chip surface area on silicon, you basically have a lower cost solution, lower switching losses, similar conduction losses, which ultimately give you a higher performing, higher reliable technology. So what do you have here is you have a portfolio that is basically unmatched by the market, from 45 or 30 watts all the way through 10 plus kilowatts. And we are in volume production all the way up to 7.5 kilowatts with liquid-cooled data center, crypto mining power supplies. So when I say 25 million devices in the market today, a lot of those are high power. And that's what customers want to see. They want to see the reliability of the technology, and we can show them that in mission-critical solutions. Thank you very much.
Thank you, Philip. Now the next turn is to Tamara from VisIC.
Thank you all for coming and listening. Thank you, Bodo, for inviting me. And I will present for you today D-Power 3 direct drive D-mode, our technology as a future of reliable power. And when we are looking on technologies, I don't believe in good and bad technologies. Each technology is as good as a product which customers are happy with. And good product is essentially a product where performance, cost, and reliability meeting in the right point. So when we are looking on performance and reliability and cost on level of technology, we are coming to volume of production. And Alex had been talking about driver markets very nicely. I do not stop on it. I want just to show that few market drivers, first and definitely fastest time to market. Consumer devices, amazing market, very good. Unfortunately, for million phones, it is a very limited volume. So this one is limiting cost and technology robustness. Next one is AI. It's a market that we had been all probably waiting. It's a great market for gallium nitride, medium power. From 1 to 10 kilowatt power is required. And this brings us to roughly 10,000 wafers to million chips. And the market of a next level is traction inverter market. It's automotive, not chargers. This is inverter driving the car. And this is market of high power, 50 to 250 kilowatt. That could be gallium nitride space, high reliability, and what is required is roughly silicon carbide performance on silicon cost. And that's possible because of volume, because this drives market to the volume roughly of 200,000 8-inch wafers per million car. Here we are talking about serious market comparable to silicon, which we want to invest to. On this, we can build really good company. So when we are going to how we to see technologies and product per market, as I said, I'm technology agnostic. I work in gallium nitride for 20 years. High reliability market is a DMOD. And I will get into details why. Consumption market, consumer, this low power market of consumer. EMOD market, cost is important. AI, frankly, I have no opinion. It's not enough data. I'm physics engineer. I'm driven by data. It's not enough yet. It could be overlaps. It could be specific. There are different voltage levels. And I think that's a place where both technologies may coexist. Just to remind what we are called D-Power 3, direct drive DMOD, it's not a cascade, it's a different, we are driving directly gallium nitride, and so threshold voltage is roughly plus 7 volt, comparable to IGBT devices. And at the same time, we have this Q2 device, which is on all the time when driver is present, and it adds probably 1.5 milliohm of resistance to the whole chain. To make it possible, we need to have fairly low resistance of gallium nitride. And this works. Before explaining why, I want to show you results. And this one I am happy to share. These tests had been completed about 2 weeks ago before this conference. Full WLTP cycle, which stands for Worldwide Light Vehicle Test Cycle, mimicking the whole cycle of electric car. It's a couple of hours, different torque, different RPM. We measured here only driving, not braking, but it's good enough. It had been done on a friendly car maker site in Europe. That's as much as I can say. Everything done in this box had been done inside of VisIC on 2.2 milliohm modules on first generation. And on this first generation dies, we had tested, you can see, above 99.3% on a majority of cycles. So this is still first generation. It's time to a lot of place to improve, because currently we are testing second generation dies. And all of this had been done 400 volt voltage, 350 amps RMS. We got to 139.6, practically 140 kilowatt, which is driving power for driving passenger car. We stopped there, so we can possibly go for 400 amp with these models, but we run out of time. It will be to continue. And when we are talking about Gen 1 Plus or 1.5, we are talking about lower RDS(on) devices, and on these devices, 2 devices in power able to provide 350 ampere peak on a double pulse 400 volt. This is the first modules done. Same technology can work also on much lower power and deliver power to AI on a power rack, essentially triple power on the same footprint. That's a vision that we have, and you can see here 22 milliohm device working with very high efficiency, delivering 10 kilowatt of power. And why is so? Why this technology and DMOD is reliable? Here I want to refer to group, very good one of CPAS, Virginia Tech, of Professor Llew. They made significant study of making, I need to go faster. You can refer to these papers of this group. Just look on this. These are breakdown voltages, static and dynamic. They must be comparable to incumbent. E-mode, all companies had been tested here on 650 volt. It's not because of companies, it's because of fundamental limitations of technology. And just to go through, we are doing modules. So this technology is implemented on modules, active short circuit protection, slew rate control, all required things to making inverter. We also have dies for lower power. We're thinking to get into power supplies and package dies with the same reliable high power transistors. And that's, thank you for attention.
Thank you, Tamara.
My pleasure. My pleasure.
And now we continue with Balu. Balu from Power Integrations. Welcome, Balu.
Thank you, Bodo. Thank you for inviting me. Let's see. Okay, good afternoon, everybody. I'm going to talk a little bit about what we do in GaN. One of the things we really believe in as a company is integration. I think integration brings the best out of GaN. For example, this is a real power supply that's in the market. It's a notebook power supply. And you can see this is a discrete solution with many, many ICs and components, including optocouplers, SR drivers, and protocol chip. And with our set of technologies and packaging and FluxLink isolation, we're able to put all of those shaded areas into a single chip, which is a small SMT package. It's about 9 millimeters by 10 or 11 millimeters. And it is able to deliver 250 watts with no heat sink. And that package is only capable of dissipating 800 milliwatts. And this is made possible by GaN, but more importantly, GaN integrated into a package with all of the controllers and FluxLink isolation technology. So by integration, we are able to optimize the performance of GaN. So if you compare the efficiency of those two circuitry, you will notice that the efficiency of the PowiGaN is substantially better than the discrete solution. And the reason for that is the integration allows us to perfectly match the GaN to the controller. We can control the DVDT so it's optimized. We can also control the scheme to get the most efficiency out of GaN. What do I mean by that? The FluxLink technology that is proprietary to our company, we are able to control both the primary and secondary switches very precisely to get the highest efficiency. We can also optimize the DVDT and the drive to the GaN so that you get the best efficiency for a given power level or given device. In fact, the efficiency of the GaN flyback GaN converter is so high that up to about 100 watts, it's actually more efficient than a complete resonant LLC power supply. And that's because we provide a active clamp circuitry that recovers the leakage energy, and so that you are able to get very high efficiencies. Now, above 100 watts, you will see that the LLC does give you a slightly better efficiency. And the dark area you see is the area where you will need a heat sink. So with the switch, we are able to deliver up to 200 watts with no heat sink. I said actually the newer ones can go up to even 250 watts. Okay, so when you talk about efficiency, you just can't talk about just a switch. You really have to look at the system. Because other than adapters, if you look at any embedded power supply, there is more than one output voltage. And the way it's derived is that you take the output voltage of the power supply and you use a number of DC to DC converters to get different voltages. You may need 5 volts for a certain logic. You may need 30 volts for a LED drive, if it's a backlighting in a display. And the problem with this is not only it costs you money to put DC to DC converters, and you need more magnetic elements, but look at what happens to the efficiency. Using GaN, we are able to deliver 92% efficiency, but once you put the DC to DC converters, your efficiency of the total system drops to 80%. Now, using a very clever control technology, we are able to completely eliminate the DC to DC converters and control each and every output, whether it's constant voltage or constant current, independently with a single magnetic element, which is a transformer. So in doing so, we have increased the efficiency by 10%, and at the same time dramatically reduce the component count. And this is where you really see the benefit of integration. So switch alone is not sufficient. You got 92%, but you lost it by putting DC to DC converters in front of it. So what's the point of using GaN if you're going to lose the efficiency anyway? And this is our latest product. We introduced this a couple of months ago. It's called Mux 2. And by the way, each cycle, it decides how much energy to deliver to each and every output. And it's able to do that because of our FluxLink technology, because we can precisely decide how much energy is delivered to the output and where it goes in each cycle. Okay, I'm going to talk a little bit about where GaN is and where I think it's going. This is probably quite common to, well known to everybody, that the GaN overlaps with both silicon and silicon carbide up to certain power level and voltages. Now, I'm specifically talking about our GaN technology, which is PowiGaN. So it currently overlaps up to certain voltages with silicon carbide and up to certain power levels. And of course, there are pluses and minuses. The GaN has higher performance, but it cannot achieve the same voltages as silicon carbide yet. Efficiency, of course, GaN is better than silicon carbide, even though silicon carbide is better than silicon. Of course, cost-wise, silicon is cheaper than GaN and silicon carbide, but silicon carbide is substantially more expensive than GaN. And that's very fundamental because it takes a lot more energy to build GaN. Now, going forward, we are pushing not only the voltage, but also the power level to much higher levels so that you have a switch, GaN technology, that can compete very well with silicon carbide. As I mentioned, GaN is a much more sustainable technology because you don't need as much energy to develop, manufacture GaN. And also, it doesn't require a lot of capital investment to build capacity. You've seen a lot of companies putting billions of dollars in building silicon carbide capacity. That's because they need very specialized equipment to operate at 2,500 degrees centigrade. GaN uses standard silicon technology temperatures. So to date, we have 750 volt GaN, 900 volt GaN, and 1250 volt GaN. And by the way, these are qualified for automotive. And so we already are in the automotive business. Now, with the current technology, we can address up to about 10 kilowatts, maybe 15 kilowatts. When you go beyond that, you have a current challenge, if you will. We can already achieve voltages that nobody is commercially offering today. But by increasing the current level, we will be able to go to much higher power levels. So we are looking at, in the future, going to power levels that will address the main drivetrain of the EV. With the current technology, we can address things like data centers, the server power supplies, and also the OBC and the DC to DC conversion. But with the next generation technology, we'll be able to go to much higher power levels. Of course, people think of GaN, they always think of adapters. It turns out 90% of the designs we work on are not adapters. It just takes a little bit longer to get into appliances, industrial applications, and so on, and data centers and so on. Well, thank you.
Thank you, Balu. Now, Llew Vaughan is the next presenting from Navitas.
Hey everyone, my name is Llew. I'm from Navitas. I'm going to have about 4 or 5 slides just to go over the future markets of GaN. So, just in case you don't know who Navitas is, we are a pure play wide bandgap supplier. We offer GaN and silicon carbide. For the GaN side, we've shipped over 175 million pieces. We have a series of family series. The latest is our GaN safe, which is for high power applications, down to 25 milliohms with short circuit protection. Now, I've got 4 slides on the market. The first slide, key slides, which shows the growth from now and then 5 years from now. Obviously, the first one is travel charges, where we are the leader in that. With travel charges, it started in about 2018 with GaN. It started around about 50 watts, but the phone makers have kind of differentiated with their phones to offer faster charging, charging within 10 minutes from 0 to 100%. And you can see they go to like 240 watts now. So if we look at the GaN market in 2019, for mobile chargers, it was just over $10 million. If we look at the GaN market as of last year, it was $158 million, so you can see the huge rise in GaN. Now, 5 years from now, it's predicted to be $1.3 billion. So almost a 10 times increase in TAM for GaN in these fast chargers. So it's a huge growth still happening in the charger market. And that's where we're leading. So that's low power. The next one we're going to look at is solar. We're going to kind of medium power. Now, the graph on the left shows the different types of electricity generation by type. You can see the red dotted line in the middle, that's where we are today. You can see going out to 2050, all these renewable energies are kind of going to take a large part of that. Solar is a big one. Solar is going to go up to about 40% of the electricity generated. So it's a big market to get into. Obviously, solar produces the electricity in the daytime. So you need energy storage to support and store the energy for the evening. So this is what I have. I've got a solar panel from Navitas, and I've got 3 microinverters. Now, the first 2 are silicon-based. And as of today, they can do about 350 watts on that microinverter, switching around 200 kilohertz. Now, the top one, this uses a Navitas GaN solution. We can almost double that power density in a smaller size. And we can switch up to 1 megahertz using our bidirectional GaN. So what does this mean to the consumer? It means that you can use less higher power panels on the home. You can use, for this example, 8 panels instead of 12. So there's a benefit for the consumer. If we look at the markets, as of last year, the solar market for GaN was about $5 million. And in 5 years from now, we're looking at $33 million. So again, this 6-7 times growth in GaN just over 5 years in solar. The third slide, which everyone's talking about right now, is AI, data center, power. As of 2020, I'm using NVIDIA because everyone talks about NVIDIA. So NVIDIA Grace Hopper in 2020 was about 350 watts on a GPU. Typically, a power server power supply will power 10 of these CPUs. So you see a lot of 3.2 kilowatt power supply units out there. Now going forward, we've all seen the announcements from NVIDIA. They're getting more power hungry with AI. The more compute power is required. It's doubling in power requirements. And the recently new Blackwell NVIDIA is looking at a 1 kilowatt on their GPU. So we have to support the power of that. So all of these power supply units are requiring, 10 times the amount of power, 10 kilowatts of power in comparison to what we have today, which is about 2.7 or 3.5 kilowatts. So the AI is a huge market. It needs power to support it. As of last year, the GaN market for data centers was 27 million. And 5 years from now, we're looking at a huge growth of over 230 million. And this is where GaN also, shows its true benefits by switching very fast, increasing power density, increasing efficiency, reducing cooling requirements. And this is where Navitas has its GaN Safe product line. Come to our booth, you can see our AI roadmap, which looks at 4.5 kilowatts, 8.5 kilowatts, 10.5 kilowatts. Okay, my last slide is EV. Everyone talks about EV, not so much this PCM, everyone's talking about AI, but everyone's been talking about EV. And briefly, if we look at the OBC, the onboard charging, and the infrastructure for roadside charging, today or last year, we're looking at about 10 million. And then 5 years from now, it's almost 500 million, 485 million. Huge growth for GaN in automotive. So I think with that, in summary, I've touched on 4 key markets. There's huge growth for GaN. GaN is just really about to take off right now, and it's a very exciting time. Come to our booth, Navitas. We're over there somewhere, and we'll talk more. Thanks.
Thank you, Didier. Is now our next speaker from Nexperia.
Oh, no, we skipped a little bit. I'm sorry, Harald.
Thanks, Bodo, and
Didier.
good afternoon, everyone. I'm from Nexperia, and I'll be covering the GaN wide bandgap design, the future of power. So obviously, we know that the GaN is a disruptive technology. It came, and it's been in the research. For the fundamental aspect that it was trying to achieve is the highest power density. And to have the technology to take the best of the technology, you need also complementing packaging to go with it for industrial and also for the high demanding automotive market. So this obviously is one of the strengths of Nexperia, where we have got a very large business with the automotive, where we have got this high reliability perspective in every technology that we bring. Obviously, this is one of the common slides you all see, but with a little bit of difference in different areas. But what it is saying that all the technology, starting from diode thyristor and right up to silicon carbide, then the evolution of this GaN came in and bringing one of the highest possible power density and efficiency, and it started going into different direction, starting at 40 volt right up to 700 volt. Currently, you will find GaN products in the market, and we also brought these products in the market for this GaN. And wherever there is a switching, the GaN benefits every application. We are continuously getting the customer request from such a wide variety of applications, including sewing machine and the welding machine, the white goods. All these areas we thought we'll never see any GaN expectation, but it's coming and looking into. So the possibility has enhanced so much that people started looking into using GaN. Even in your surfing, the people will be using the GaN. We started using our low voltage devices, but the GaN can make the life very simple for high power. So obviously thinking beyond performance, it is the availability and the cost where the Nexperia comes in with a huge infrastructure where you can have the volume growth that is required by the market and with a reliable supply chain, and that's where beyond the performance, we'll have to look into those aspects that where we can give the comfort for supply chain reliability. Just a little bit refresher why the GaN is the future, because the GaN has got the highest bandgap, the highest critical electric field, and the highest mobility that doesn't suffer at high temperature either. So all this brings the GaN where it is now performing. So just quickly looking into the GaN landscape, we know that the GaN has got the cascode or the D mode complemented by the superjunction low voltage MOSFET and also the E mode. And we believe the GaN has got a coexistence of this E mode and the cascode devices in different quadrant. You can consider for the low power in the low voltage and the high voltage, GaN is well positioned. The low voltage but high power GaN low voltage E-mode devices is well positioned too. But on the high power, high voltage where the cascode comes in, because cascode fundamentally brings significantly better specific radiation compared to the E-mode devices. E-mode devices, we see that the specific radiation cascode device, because it's a dedicated 2-DEG, where you can actually get a much better specific radiation. Currently, our cascode devices are almost half the size of the equivalent E-mode devices at high voltage, where we position our cascode devices. So we have got this E-mode and the cascode all covering the full spectrum of the landscape of the application space. And if you can look into all the application that you can see, basically GaN can cover anything that is switching at the moment. Going beyond the 400 volt or the 650 volt boundary, because there is higher voltage platform like 800 volt, where the multi-level inverter, we consider it to offer better frequency capability and also higher efficiency that the GaN can offer. Or we can go with the, this is like a 3-level attenuator point clamp configuration, or you can have the hybrid with the silicon carbide and GaN, or you can have the GaN only multi-level where you can use the GaN because of the voltage breakdown. Then you can actually go for higher DVDT and without causing any problem to the motor winding, which will give a headache to the designers. Just quickly looking into the GaN efficiency actually outperformed the silicon carbide. We have seen that because GaN doesn't suffer at high temperature, GaN doesn't suffer the switching losses. And we have done temperature switching with GaN, we didn't see any difference in the crossover losses where the GaN at high temperature. In the 48 volt, 12 volt, where Alex already covered that the E-mode GaNs are well positioned, where the high voltage and high current, our cascode GaN. This is a single high, single low half bridge where we have managed to get the 150 amps, around 5 million die, a single die. And you can see that the 500 volt and 150 amps with a very smooth switching curves with obviously dedicated Kelvin pin. And having a very good technology is not the solution always. You need to have a complementing high performance package. And what we bring in the market is the CC pack, all copper clip package, which is complementing with a very low RDS(on) and low inductance. So this package actually offers less than 1.5 nanohenry inductance. And because of the gull-wing type of legs, this gives a huge benefit of the board level reliability. Even about 3 times ACQ11, we don't see that any problem with the board level reliability with this one. And obviously the problem of the cascoding, the low voltage silicon die on top of the GaN die is taken care of by ourselves. So as a user, you can actually use this one without any problem with a very high threshold voltage capability of our device. So with that one, thank you very much. We have got the booth, so you can come and visit us in the booth there.
Thank you, Didier. Now it's turn for Harald Parzhuber from Texas Instrument.
1, 2. Good. Thanks, Bodo, for inviting me. Appreciate that I get the opportunity to speak for Texas.
Go ahead.
Go ahead. Good. Thank you.
Thank you.
So we at Texas Instruments, we drive also the philosophy of system integration. So we add more features to our GaN devices. It's not just a GaN FET in enhance and cascode mode. We add gate drivers to it. We add functions like protection. We add features like temperature sensors. So integration is a path that we are going down. So what I'm going to introduce to you today is a new product where we drive the integration of features and functions more and more forward. So I'm going to talk about an intelligent integrated power module, IPM, that is actually all GaN based. And this is actually the first on the world that is IPM based on GaN for motor drive applications. Let me spend a few words on why this is a big deal to do integration for a motor drive based on GaN. So there is, depending on which region you're looking at, there is always a demand for higher efficient HVACs or appliance applications. So there are standards that are dictating or defining basically the overall system efficiency needs to go down, and you have multiple knobs to turn on that. One is you redesign the motor to make it more efficient, or you work on the motor drive. We as a semiconductor supplier, we work on the motor drive side of things, and this is how we came up with the IPM that has better features, better efficiency, and overall improves the efficiency of the system. So designers have the challenge. How do they do a design that is more efficient at a reasonable low cost and addresses the form factor as well, just to make this overall equation for the overall efficiency work? So what we had been coming up is basically a design, the DRV 7308, integrated three phases, half bridges, motor drive IC, which has a 250 watts efficiency of 99%. And that's a big deal compared to the IGBT-based solutions. In addition to that, GaN offers that you have a low dead time. Why is the low dead time a big deal? If you compare this to IGBT-based solutions, you see dead times that are more in the 800 nanoseconds, maybe microsecond. A big dead time is distortion in the system. Distortion in the system means noise. This could be audible noise depending on how fast you operate your design. By reducing the dead time, you have less distortion, which is positive for audible noise, and also to keep the ripple currents in a motor drive, in the motor itself, small, which is good for the reliability of a motor. And overall, we had been able to reduce the size with this device significantly. So compared to existing solutions, we were coming down by 55%, or around 50% for a complete system integration. Let me spend a few words on the efficiency, because this is one of the main drivers why we choose GaN here. This graph shows basically over the output power, the efficiency we achieve. In red, you see the new IPM DRV7308, which is GaN-based, and we have looked at a comparable IGBT IPM module. We see that we have around 99% efficiency versus a 97% efficiency. In absolute numbers, 250 watt, 1% losses means 2.5 watt, compared to 7 watt, maybe 7.5 watt on IGBT-based. You don't need a heatsink for that design. And that design actually works at 250 watt without any heatsink. And by the way, if you have time, TI booth is there. We can demonstrate it live there if you're interested in. Now a few words about the solution itself, what we all integrated. It comes in a 12 by 12 millimeter package, QFN package. We have integrated the 3 stages, all the gate drivers, all the protection. Additionally, for single shunt current measurement, integrated op-amp, which allows you to optimize the design for your particular needs. With that, I would like to thank you for the attention.
Thank you, Harald. Now, Giorgia, the final presentation for the GaN session.
Thank you, Bodo. Thank you, everyone. Now, the good thing about being the last is that everyone has touched on the key points. The negative thing is that everyone has touched on the key points. So let me go through what we have and show you my view of why this is not working. And maybe I show you. So let me just introduce, talking over the key slide. The topic of today's panel was, what's the future of power electronics, with a focus on gallium nitride? I would like to use 2 keywords here to look at the future of power electronics for GaN. One is integration, which has been used before. Integration which goes, in my view, alongside with innovation. So there was a question yesterday at one of the panels about the consolidation of the GaN market. Is the GaN market being consolidated? Well, my strong answer to that is absolutely not. And the reason for that is because of these 2 keywords, integration and innovation, that GaN, and in particular lateral GaN, provides. The second point is on the sustainability, and today I would like to show to you a different perspective from what we have seen until now, and just introduce to this audience of engineers and executives what GaN can do in terms of sustainability and what companies in general can do in terms of promoting efficient power electronics. Now, Cambridge GaN Devices is the new kid in town, so you might have heard of us. Hopefully you have seen our presentation about the new product being launched yesterday. We have been in the market for consumer electronics until now. We are now going high power. And our technology is called ICE GaN. You see here a few elements of the technology. In general, as I said, it's based on integration. We believe that the lateral GaN technology can help providing not only ease of use, but also smartness and protection. So we have the high power transistor and we have logic integrated, all in GaN. Now, the beautiful thing about the whole circuit, I won't spend too much time on it, but I will just focus on key things. We deliver with GaN the ability to use GaN with any silicon gate driver, with any silicon carbide gate driver, and on top of that, we add a current sense, but we also make the transistor extremely robust. Those of you that were at the introduction of the products might remember that we have demonstrated extremely robustness all the way to 75 volts on the gate in dynamic conditions, of course, which is higher than what any silicon carbide or silicon IGBT can deliver. So that's all integrated. And by the way, the circuits, one question we usually get is how much space does integration occupies? Well, it's absolutely negligible. So it gives you the benefit of the ease of use. It gives you the benefit of the reliability and robustness on the gates. That is one of the most sensitive parts of the E-mode transistor. And at the same time, it's absolutely scalable in power. And that's what we have done in the P2 series that we have launched just yesterday. Now, today's silicon and silicon carbide gate driver, and that's a comparison based on a typical discrete type of technology. So the GaN technology requires a system, a complex system to be driven, and that's just with one transistor. If you look at topologies for the high power, then you have half bridges, you have much more complicated topologies that require a number of components in excess to make the GaN or the transistor as reliable as needed. Today's technology with silicon and silicon carbide do not require that, and that's exactly what GaN has delivered. And it has delivered it in the low power, it has delivered it in the high power. Again, the new products, P2, in two different type of packages, bottom side cooled and top side cooled, are available as of today. Now, just a few words on, and we have a little bit of an animation there, on what that means and why can we claim that it's easy to use. First of all, we had some claims about threshold voltages already. So our threshold voltages as high as 3 volts, so comparable, again, with all the other technologies, not, again, discrete. The outer voltage, so the voltage you can apply on the gate of the transistor is as high as 20 volts, even above that voltage. It's absolutely robust with no issues whatsoever. Those of you that have worked in GaN, we had people working on the physics of GaN, know that if you apply more than 7 volts, you have strong reliability issues. So in our case, that is not happening. The inner gate voltage is temperature dependent, as you see, and there is absolutely no need of negative voltage or complex gate driving in the system. On top of that, it's absolutely robust, as I was mentioning. And this all leads to a series of advantages in terms of bill of material and the space that the overall technology occupies on a PCB. Now, I've mentioned about the P2 products we have launched yesterday. We have two new on-state resistances, the 25 million and 55 million. So going to the high power, going in particular into markets such as the data center markets, the motor drives, and by all means, come and visit us at our booth. For those of you that do not know where we are, you just need to turn your back. It's right behind us, so very easy. Please come and visit us. But before I move from this topic, I just would like to focus on the second point I was mentioning before, on what can GaN do and why it's important to look at GaN for the future of power electronics. And that is because of the energy efficiency. And now, allow me to say a few things before I move directly to the next slide. We talked about AI. We saw the market figures. We saw that it's, everybody's talking about AI. Not many people are aware that the power is needed, I mean, not in this conference, of course, but outside this conference, how much power is required to power up AI. In a single rack, now the requirement of power is being increased by at least 10 times. Now, if you want to make sure that we don't dissipate all the power on the power transistor and the system, so I agree it's a combination of power and system, but if we want to make sure that most of the power goes to the actual appliance, then we have to use efficient technologies. And on top of that, we have to make sure that the power density is also kept as high as possible, because you really want to use those racks for the data centers for the computational parts of the electronics, not really the power. Now, what happens if we use GaN in our data centers? These are just some numbers, again, to give a different perspective for the one we have looked at until now. There is a huge impact that GaN can have in terms of energy efficiency. So we, as a community, we have the duty, I would say, to educate the general audience in terms of what it means using GaN. And that's one of the things I care quite a lot about, because GaN is not just about the next technology, but it's much more than that. It's about being the technology that can reduce the energy losses on applications such as the data centers. And of course, we can talk about CO2 emissions, but nobody knows what cubic tons of CO2 is, so there are very nice websites making conversions of how that translates into things that are tangible for us. And I just want to leave the audience with the last slide, which is what can we do as a company that as companies that are delivering energy efficiency technology. So I didn't mention we are the new kid in town, but we are not working only on the technology. We want to lead as an example, as a company that really delivers the most energy efficient products for high power, but at the same time is looking at what else GaN can do in terms of energy efficiency. GaN is, we had something, I think Balu was mentioning about energy efficiency in the process. So GaN requires much lower temperatures. So the whole process of GaN is much more environmentally friendly than silicon carbide. And on top of that, we are committed to sustainability as a core value. There is a lot of green here around. If you look around, we believe in that green. We believe in GaN as a sustainable product. And in particular, there are several things that companies can do for pushing that point of the agenda. So just to summarize my talk before I leave you to the next panel, this was a quite intense panel in terms of know-how. The key things, please come and visit us right behind you, CGD with a plant coming from the top, so you can't miss us. And the second, we have launched P2 products, 25, 55, in 2 types of packaged, where we demonstrate that our thermal performance is much better, not only of the other GaN discretes, but also of silicon carbide. So thank you very much.
Thank you very much, Giorgia. Thank you, ladies and gentlemen, being here for the GaN session. Now, stay tuned, get my magazine, and looking forward to our White Bandgap event in December.